Okay, welcome to the second part of our projectile motion discussion. So, we've talked about projectile motion, we've looked at a free fall type of motion and something that maybe has some initial velocity and some horizontal component to it. What if we launch something, this projectile, at an angle? The thing is not going just straight out, it's going up at some angle. How do we solve these problems? That's what we're going to learn in this video. All right, let's go back to our kinematic expressions. I wrote some of them down for us right here. From these and from knowing something else here, these equations are derived. These are the equations that are going to be really useful and helpful for us when we're looking at making calculations about projectiles that are launched at angles. Okay, how do we know these things are true? Let's just go back and review here. Let me pause this. If I have a projectile being launched here, okay, let's say at this angle, that is my resultant vector. It's going to be I'm wanting to find my initial velocity. It's going to have two components to it. It's going to have the x and the y. Right here would be the x component, vxi, and this here would be the y component, byi. But it's getting messy. All right, and this will be the angle I'm launching it at, theta. That looks terrible. I'm sorry, this is so messy. But if you'll remember, cosine theta, so the cosine of the theta is the adjacent, which is vxi, over the hypotenuse, which is the vi. This is the right angle right there. Likewise, sine of theta is going to be equal to vyi, because it's going to be the opposite over the hypotenuse. These equations then were rearranged so that the vxi and vyi, the individual components, the x and the y components, those variables were separated out and just equal to the rest of it. So that's where those equations came from. I'm not going to go through this because the video gets awfully long when I do that. But these kinematic equations from last unit are directly how we end up determining each one of these equations over here. We are simply substituting components here into them. See if I can quickly go through where some of these came from. We know that our horizontal velocity right here is a constant, the same as it is when it's the initial horizontal velocity. Well, that's just right here. Our initial horizontal velocity is going to be equal to the initial velocity times the cosine of theta. So that's just what was written right here. This equation right here comes from a combination of what we know up here and this equation, velocity equals change in distance over change in time. This was simply rearranged to be delta x, the change in displacement, is going to be equal to the velocity times the change in time. And in this case, our velocity is going to be whatever the initial velocity times cosine theta. That gives us our displacement in the horizontal direction. Right here, this equation, this comes from a combination of this equation and this understanding here as well. We know that we're going to be talking about the y direction here. So we are looking at the final velocity in the y direction is going to be equal to the velocity, the initial velocity times sine theta, because that will give us the initial velocity in the y direction, which is this. So we substitute that in to this portion. Negative g is substituted for a, and then we have a delta t. Again, this is a combination of this kinematic equation plus this understanding from our trig formula. And last, I apologize again here, I put the wrong equation in here. This is a displacement with constant uniform acceleration with a different unknown in it, and this in conjunction with this trig function yields this particular equation. So let's do a practice problem together. Let's suppose that a golfer is sitting around practicing driving balls off of a cliff and into the water below. The cliff is 15 meters up from the water, and the golf ball is launched at 51 meters per second is its initial velocity, and it's launched at an angle of 15 degrees. How far does the ball travel horizontally before hitting the water? So again, we're going to choose our coordinate system, define, sketch, label everything. Really critical component in physics. Always, 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 always do this step. We're going to choose our equation or equations. We're going to calculate and then evaluate. All right, here's our scenario. We have our golfer. He's going to launch the golf ball like this. We know a few things. We know 15 meters from the water is how high the cliff is. We also know the angle at which the ball is launched, 15 degrees. We do not know how far the ball lands away from the cliff, so that would be our unknown. And that's a question mark there. And we also know one other piece of information. We know that the initial velocity is 51 meters per second. So those are my different variables, the things I know and the things I do not know. I also know, obviously, G is 9.81 meters per second squared. That is something else that I do know. So let's go to the next page and start on this problem. All right, this problem is way too hard to try and solve. All that motion all together is too complex, too complicated. We're going to break this up. When we have a problem like this where we have something being a projectile being launched up at an angle, when it gets to the very top of the trajectory, that's a really nice breaking point. We're going to divide the problem into two parts. We're going to look at what happens prior to reaching the top of the trajectory, and then we're going to look at what happens on the way down. That makes it really a lot more simple. So let's look at, we can call it part one of this projectile motion. For part one, we're going to use one of our equations that I just listed in the previous frame in order to, again, solve for the time. The one thing we don't know in all of this, we don't know time. In our part one situation, we do know the final velocity in the vertical direction, in the y direction. How do we know that? Because as this ball is going up, it reaches a point here where the velocity is 0 at this point. It doesn't go up anymore. And actually, for one moment in time, it has a 0 velocity in the vertical direction, okay, at that point. It then proceeds to go down. But our vertical velocity at this point, the final velocity in part one of the motion, will be 0. So we know this is going to be 0 meters per second. We know the initial velocity because we were given that in the problem. It is 51 meters per second. So our initial velocity is 51 meters per second. We also know the angle at which this trajectory was launched, 15-degree angle. So we're going to say sine of 15 degrees. That's our angle that the ball is being launched. We also know acceleration due to gravity, 9.81 meters per second squared, and I am running out of room. but we do not know delta t. That's an unknown. Now, I'm going to let you work through the algebra on your own. Pretty much, it should be fairly simple. This is minus all of this. So the first step would be to multiply these two terms together, find sine of 15 degrees, multiply it by 51, then subtract this term from this side. It will be a negative whatever that is. After that point, you can divide both sides by a negative 9.81. That will give you your delta t. I can also write this problem, here's just without our little picture, if that makes it easier for you to understand what this is what is happening on this first part 1 of the trajectory of this ball. Now, a couple of things I need to start thinking about. I need to find out basically how far horizontally the ball is going here, and then how far horizontally it will go here. In order to do that, I am going to need to find out how high the ball travels as well. So I'm going to need to find its vertical, the magnitude of its vertical displacement, as well as the magnitude of its horizontal displacement, because when the ball falls down here, I'm going to need to know how high it traveled to know how much time it will have to travel out this direction. So I'm going to go ahead and use two equations from the equations I gave you on the previous slide that will help me determine the delta y and the delta x. This is the equation I'm going to use for that. It simply copied it from that previous screen, and now I'm going to plug values into here because I do know all these things. So I know my initial velocity, 51 meters per second. I know theta is going to be right here, 15 degrees, and I know my time, that is going to be 1.35 seconds. I also know acceleration due to gravity, 9.81 meters per second squared, and again, my time is 1.35 seconds. And I just wrote all that in for you. Those are the numbers I just described, and my answer ends up being 8.88 meters. Now I need to find the change in horizontal displacement, the delta x. I'm going to call this delta x1 for phase 1 or part 1, the first part of our problem solving. And I'm going to use one of the equations that were listed for the projectiles. Here's the equation I'm using. I know the initial velocity is going to be 51 meters per second, theta is 15 degrees, and time is 1.35 seconds. And when I punch that into my calculator, I get 66.5 meters. That's the horizontal displacement. Now I am ready. I found the time it takes for the ball to travel from here to the top of the trajectory. I found out how high it went up, the delta x. I found out how far it went out, the delta y up, and then how far it went out, delta x. Now I'm ready for part 2. All right, for part 2, I just simply rewrote what we discovered for part 1, our change in horizontal position and change in vertical position. So for part 2, we need to know, again, we're going to need to find out how long it takes so that we can solve eventually the problem of how far it takes to get what the horizontal displacement is going to be. The first thing we'd like to do, though, is look at this problem will be solved in a similar way as we solved our free fall problems, where an object is being launched simply horizontally. Don't forget that we have horizontal velocity going on right now. This isn't just dropping straight down. There is some horizontal velocity. At the top of the trajectory, we are beginning with 0 vertical velocity, but we do have some horizontal velocity. So this is like it's like an object being launched horizontally only. So that is how we're going to solve this problem. The first thing we'd like to know, because we have the information for it, we know delta y here, the position up and down. And we know that because we went up 8.88 meters. We are now going to go down 8.88 meters before we continue all the way with our 15-meter cliff drop. So if we add those two together, the 8.88 meters here in the vertical distance and 15 meters here, we get our delta y. And it's actually, they're negative because they're going down. So it would be a negative 23.88 meters. Now, since we know the vertical displacement, we can use this equation that we used when we were talking about projectiles earlier. The delta y, we can substitute this in for delta y. We know what gravity, acceleration due to gravity is. This will enable us to find time. How long does it take something to fall this far in the vertical direction? So we can go ahead and substitute those numbers in and solve for delta t. So I ran out of room a little bit there, so I didn't get the parentheses around my delta t. But clearly the negative values cancel on both sides. I can multiply both sides by 2. That gets rid of this term. And then divide both sides by 9.81. Then I can take the square root of both sides to get my delta t. I can now see that it takes that ball 2.2 seconds to go from the top of the trajectory into the water. I'm now ready to try and solve for delta x, and I know that it didn't do a very good job here, but this is the y component. I have delta y is negative 23.88. I want to find my delta x. From the point where it's the top of the trajectory to where it hits the water, I would like to find delta x. And I can do that with one of my equations from before. So I can plug my values in here very simply. Remember my velocity, I still have that 51 meters per second velocity that I'm going horizontally with. That hasn't changed. I'm still horizontally going that much. So that's still my velocity in that horizontal direction. But it's I get 2.2 seconds to be going that velocity now. In the second half of this problem, I get 2.2 seconds to continue going 51 meters per second before my vertical velocity runs out and I hit the water. In which case, my change in horizontal displacement is 112.2 meters. I didn't tell you there was going to be a part 3. Part 3 is just finding the answer. The question to this problem is, how far out from the cliff is that ball going to hit the water? And that's what we're going to figure out in part 3. We're going to look at part 1 and part 2 of this ball's motion, and we're going to add its displacement, its horizontal displacement from part 1 with the horizontal displacement from part 2. When we add those two numbers together, remember here's our x1, 66.5 meters. That's how far it traveled right there. And then x2, 112.2 meters is how far it traveled right there. We add them up together, and we need to make sure our answer considers sig figs. We're limited by 2 sig figs, so it's 180 meters. Depending on some of your rounding, you may end up with 170 meters if you work this problem through on your own. Phew, we got through all that calculation. Good going, guys. I hope you could hang in with me, and you'll get to practice some of these on your own. So, review. Projectiles launched at an angle. We're going to use the equations which combine trigonometric functions with kinematic equations, those equations that I gave you, that nice little box full of them, and you don't have to memorize them. Lucky for you, you will get to use these equations, and you don't need to commit them to memory, but you need to know how to use them. And you need to know how to solve these problems. And to do that, you break the problem down into its simplest parts. You're going to treat a free fall part of the problem separate from a launching at an angle part. Remember to solve for the horizontal and vertical components separately in each of those parts of the problem. Remember that the change in time remains the same for both the horizontal and the vertical component. If you want to go for some advanced ideas, create your own problems for projectiles launched at an angle and solve them. I look forward to seeing you in class and helping you work through some of these problems.